Okay, now we've made our way to processing in memory. It's another fascinating topic, and we're not going to be able to finish it in the remaining time today, but we'll continue tomorrow. And this is another very, very hot area right now in computer architecture. And this really spans the entire stack, all the way from the lowest levels of the devices. How can you design a device that can process data while also storing it? And all the way to algorithms. How do you design an algorithm that can take advantage of the processing capabilities at the devices or cores that are really inside or close to memory? So we're going to do a treatment of it, but clearly we're not going to be able to cover the entire span of it. I'm going to give you examples of things. But remember, these were some key directions that we were talking about. We've talked about security, reliability, safety. Rowhammer was a very good example. We talked about latency quite a bit. Today we're going to talk, and we talked about genomics, if you remember Mohammed's lecture. Today we're going to focus on energy and latency a lot. And processing in memory is actually one way of designing much more energy efficient architectures and low latency architectures at the same time. Remember this guy? Maslow and his hierarchy of needs. I motivated Rowhammer or reliability by saying that that's the first thing that needs to be satisfied if you want to live, right? You need your physiological needs and safety and security needs satisfied. But one of the physiological needs is also energy. So it's not clear which one is more important, security or energy. And we're going to tackle that big physiological need, both for humans as well as systems in general, right? And we want to minimize that as much as possible. Because if you're energy inefficient, you're actually wasting a lot of things on top also. Okay, so basically another way of posing this is, do you want something like this? Actually, I don't know where this is, but Switzerland is kind of like this. It's nice. Or do you want something like this? This looks kind of like 1940s, 50s Pittsburgh. Not that great. You don't want the world to be looking like this. So there's a huge impact of energy on everything else that we do in life, and sustainability, which is becoming a much more growing problem. Of course, there is a lot that goes into this clearly, but computing is becoming an increasing fraction of that a lot today. Data centers, for example, are consuming, I think I read reports saying that maybe 2 to 3% of the entire world's power is spent on the data centers today, and that's going to increase a lot. 2 to 3% is a lot, actually, if you think about the data centers. Of course, there's a lot more energy waste in other things as well, which we can talk about separately, but we're going to focus on computing today. And I think processing in memory can help us avoid this sort of future. And let me tell you why. So I actually give longer talks on processing in memory. I base the talks based on my lectures and improve my lectures based on the talks. So it's a very synergistic, symbiotic effect. This is one example of the talk. I'm going to cover the lecture with the same structure of the talk. So I usually motivate, we've already covered the major trends affecting main memory. I usually motivate the need for intelligent memory controllers from two directions. One is bottom up. Basically, today's circuit scaling, device scaling issues are forcing us to have more intelligent memory controllers. And I've given you a lot of examples of this, right? For Rowhammer, for example, an intelligent memory controller can give you better protection. And there's a push from circuits and devices to have more intelligent memory controllers to deal with reliability issues. Similarly with latency, like we've discussed, right? If you look at the latency, a lot of the ideas that we talked about require more intelligent memory controllers. If you want to reduce latency, maybe doing it at the device level is very hard, but if you actually have an intelligent memory controller that can profile your latencies and figure out the reliable operational latencies, then that's good. So there's a big bottom-up push from the circuits and devices that push us for having more intelligent memory controllers. Reliability is a key concern, but latency is another example, or power and energy like we've discussed earlier. We've covered that a lot. I'm not going to cover that again. But there's also a huge top-down pull, meaning that systems and applications are pulling us to do something completely different today, maybe have intelligent memory controllers, right? And I'm going to motivate that right now. And usually, if you want to fundamentally change the paradigm or insert that paradigm into many other paradigms that are happening, it's good to have a situation where things are actually constraining you in both directions or in multiple directions that you have nowhere to escape. And I think this idea of processing in memory is at that stage right now there's a huge pull from the devices and circuits that is pushing us for intelligent memory controllers, and there's a huge pull from systems and applications that's also pushing us for intelligent memory controllers. So maybe we have no other choice but actually have more intelligent memory devices and memory controllers. Let me talk about this top-down a little bit. And we've also talked about the top-down before, but I'm going to go into the top-down a little bit more. But basically, the observation and also opportunity is that you have high latency and high energy, and that's really caused by a lot of data movement. If you were not doing data movement, maybe you would not have as high latency and high energy. Why? Because we're moving data across long, energy-hungry interconnects, inside chips, across chips, within chips. It could be memory chips, it could be processing chips, but there are interconnects everywhere. And we've tried to reduce the latency and energy based on that, if you remember tiered latency DRAM, right? And electrical interfaces are consuming a lot of energy and latency as well. The analog interface to DRAM, for example, is very energy hungry, and the long interconnects are very energy hungry. And we're moving large amounts of data on these energy hungry interconnects everywhere. And the opportunity that we have is that we can minimize the data movement by performing computation directly where the data resides. So if you actually can do this, then you basically avoid all of this, right? These interconnects, maybe it's not as important. You can still have them, but maybe use them very, very infrequently. So that's the idea over here. This is the general idea is called multiple things, processing in memory, for example, or in-memory computation, or processing, or near data processing. I'm going to treat them to be all the same and call it processing in memory right now. And the general concept is applicable to any data storage and movement unit. For example, you could do this in the cache as well, on chip cache. If that makes sense, that's a good idea to do perhaps. In the SSDs, in the flash memory controller, you could potentially do this. Inside the flash memory chip, you could do this. Inside main memory, you could do this. Basically, wherever data resides, this general idea is applicable. You could do it inside the network interface card, for example, network controller, or wherever you're basically transmitting data or storing data, you could do computation. Make sense? And it's a general concept. We're going to focus especially on the memory, main memory part, because I think that's the harder problem in all of these. You could do it, yes, in the SSDs, network, and actually people are doing computation side network interface cards, and some other controllers. But main memory is a little bit harder because the interfaces over there are very rigid today. You could do it in your SSD also, actually. If you hack it, you could actually push computation inside your SSD. Because SSD itself, if you look at it, it's a processor and memory kind of system. Whenever you're doing computation inside the processor that is really managing the SSD, the cores over there, you're still moving data between the SSD and the processor. So you're really not doing processing inside the memory itself. You're doing near data processing because you're not moving that data all the way into the main processor, the core, right? You're really doing it inside the SSD system. So SSD is a full system by itself. Okay, and that's easy to do. Of course, if you want to do it inside the flash memory, that's a different question. Now that looks more like, it's like main memory again. Okay, so basically we're going to cover main memory especially. So what are these top-down pulls that I mentioned? So there are three key system trends which we've discussed actually to some extent before. I'm going to make sure that they're actually put together right now. Basically, data access today is a huge bottleneck. Applications are increasingly data hungry, and I'm going to give you examples of this. We've already given some examples. Energy consumption is a key limiter today, and data movement energy dominates computation today. So these are actually becoming even more constraining. And this is especially true for off-chip to on-chip movement. And we've seen some examples. So there are many applications today that demand more data access, and they're bottlenecked by memory bandwidth, capacity, latency, and everything. Clearly, latency is ignored. That's why we've looked at latency quite a bit. But some of these applications are bottlenecked by pretty much everything. And we've also talked about bioinformatics, for example. Those are actually dominated by data access quite a bit. So these may be backward-looking applications in the sense that we know a lot about them. But they're also forward-looking applications that we may not know a lot about and that we may not have imagined currently. But they're going to very likely process a lot of data. For example, the devices that are out there collecting data on whatever you may or may not want them to collect data on, they have a data processing problem. And that data needs to be processed efficiently, right? All of these IoT, Internet of Things devices, they're collecting data on everything. And if you're actually moving that data to somewhere else to process, you already lost the efficiency to begin with. Okay, so there's clearly a big need for memory performance and efficiency. These are related. So the future is really high performance, energy efficient, and sustainable. So how do we get there? The problem is, even though data access is the major performance and energy bottleneck, our current design principles cause great energy waste and also great performance loss. I say great energy waste big and great performance loss small because we've tried to reduce this performance loss as much as possible, right? We've designed processors that are very complex, that do out-of-order execution, multi-threading, prefetching, caching, very, very sophisticated techniques. And if you look at all of those techniques, pretty much all of them are dedicated to tolerating the memory latency and memory bandwidth issues that could cause problems. So maybe we could tolerate the performance loss a little bit. But the techniques we add into the systems to tolerate the performance loss are causing even more energy waste because they're actually very sophisticated techniques. Massive amounts of multi-threading, for example. You need very large register files. We've discussed the GPUs earlier, right? You need huge register files to be able to tolerate things, and you need to have intelligent switching algorithms. So I think energy is even more fundamental to processing in memory than performance because maybe you can actually get rid of performance loss in some ways. So the real problem is processing of data is performed far away from the data. And that's why we're actually having this energy waste and as well as performance loss. Whereas if you look at a computing system, it consists of three key components: computation, communication, and storage and memory. And this is actually nicely described in this seminal paper by von Neumann. This is the paper that actually introduced the von Neumann architecture. And if you look at these units in our cartoonish way of drawing them, this is from a book chapter that we've written on memory systems. I think it was in the Encyclopedia for Computing or something like that. I don't remember where it was, but it's a high-level book chapter that talks about memory systems. And if you look at this computing system, we optimized this part of it a lot. In today's computing systems, we're very overwhelmingly processor-centric. And I'm going to talk about processor here, but it's really also about accelerators, right? Today, we put not only general-purpose compute units over there, but we put a lot of accelerators over here. It's still the same. It's still part of the computing unit over here. All data is processed in the processor or the accelerators, and this comes at great system cost. Basically, we optimize this very heavily, and it's considered the master. It's obvious, right? This master says read, write, and they get what they want. And the data storage units are dumb, and they're largely unoptimized as a result of this design choice, except for some that are on the processor die. The processor die hosts caches, for example, and caches are very, very heavily optimized today. Less optimized than the processors, but very heavily optimized compared to the other memory and storage and communication units over here. Yet, it's really the memory stupid. This means that, it's really the memory. So this was actually an article, we should put this article online. This was an article written by Richard Seitz, who was the chief architect of the Alpha 21264 processor. After designing the processor, he basically wrote this one-pager article, it's really one page, in Microprocessor Report, that says, okay, we've designed this processor, it works really well, it was the fastest processor of its time actually, when Alpha architecture was around. How many of you know the Alpha architecture? Okay, maybe one or two, okay, good. Well, in some places you can actually use that, it's a very beautiful architecture actually, but it didn't, it's not used I think anymore in anything, it didn't even survive. But this was the fastest processor of its time, and basically what it was able to finish 4 instructions per cycle. And one of the things that he mentions is in one of the important workloads for this architecture, they figured out that it's finishing 1 instruction every 4 cycles. I think it was a database workload, for example. Basically, this processor is operating at 1/16 of its peak bandwidth in terms of computation. And why? Well, it's because of memory. Because it's waiting for memory most of the time. And I think he actually concludes the article by having a sentence saying that in the future, in the next decade, the most important thing to focus on in processor design is really the memory system. Of course, that didn't happen that much, but it's going to happen. Okay, so that's one example. And I would recommend that you take a look at this article. We should upload it online. It's a one-pager. It's not extremely technical, but it's technical also. So that's 1995. Okay, fast forward. We may have time to talk about my thesis. This is actually data from my PhD thesis, basically where we analyzed again, how often is the processor stalled for various reasons, including cache misses. And that's actually data based on simulation on many workloads that Intel used to design their systems with at that time. So it's a lot of traces, a lot of workloads, real workloads. And we found out that, not surprisingly, more than 55% of the time, the processor is waiting for L2 cache misses, basically memory accesses. Okay, and maybe we'll talk about run execution later on. That's 10 years later. Okay, fast forward 10 more years. And this is a paper, if you're really interested, you can prefetch and read it. But basically, this designs a simple way of tolerating memory latencies. Okay, so fast forward 10 years. This is data that Google presented in another very interesting paper in ISCA 2015. And they basically looked at all of their, according to them, all of their data center workloads classified in some way. And you can see there are really interesting ones, right? Gmail, video, ads, indexing. And they basically did a similar study, and they found out that most of the time the processor is waiting for data to come back from the processor, come back from the memory. And actually, it's doing useful work, retiring an instruction only 10%, 10 to 20% of the cycles, execution time. Okay, and there's more analysis in the paper if you're really interested. This is a good paper to read as well. So basically, I've given you a span of 20 years or so. I could increase this, but essentially nothing has changed. We're designing these processors. They're becoming higher performance, higher frequency. They're becoming more efficient in doing what they do, but they're still waiting for memory. And they will keep on waiting for memory if we keep designing them the same way, because nothing is fundamentally changing, and memory is becoming a bigger problem. Okay, so what are the perils of this? So essentially, the key realization is that we have a grossly imbalanced system. Remember, balanced design is one of the key principles in architecture. Today we have a grossly imbalanced system because processing is done in only one place. Everything else just moves and stores data. They're all dumb, basically. Data moves a lot. And this is energy inefficient, low performance, and complex, because you need to design a complex system to do processing only in one place, and that thing needs to become very complex. And as a result of this imbalance, you have an overly complex and bloated processor and accelerators, because they need to tolerate the data access from memory, which is long and slow, and which goes through a thin bottleneck. And as a result, you need to build complex hierarchies and mechanisms, multi-threading, prefetching, caching, latency tolerance techniques that we've talked about when I started the latency lecture. As a result, you become energy inefficient, low performance, and complex. Maybe you can recover some performance, but maybe not the full performance. Okay, so as a result, we have this picture that I showed you earlier in the lectures. This is my cartoonish picture, of course, right? But basically, I said that most of the systems that we design are dedicated to storing and moving data today. Computation is a very little part of the system. In this case, only the red parts. The cores are doing computation. Everything else, and even the bigger sense, everything else is doing data movement and storage. So that's the performance perspective, and also the area and cost perspective, if you will. There's a cost aspect of it that I'm not going to talk about here. The energy perspective, something happened in the light over here, but that's okay. You can still see it. Basically, this is data that Bill Daly showed in his High Peak 2015 keynote. And you could argue with the numbers over here, because this is based on some specific technology nodes. And maybe some of the things are very optimized, some of the things are not very optimized. But basically, he looked at how much energy does it cost to do particular things on a chip and off chip. So if you look at 64-bit double precision floating point operation, it's about 20 picojoules. If you look at moving data from one end of the chip to another end, it's 1 nanojoules. If you look at a DRAM read or write access, it's 16 nanojoules with some technology parameters. And I'll take the liberty of increasing that 800x to 1000x. Basically, a memory access essentially consumes about 3 orders of magnitude more energy than a complex addition. That's a lot. If you think about, okay, assume that you don't have a lot of locality, you're doing a lot of random accesses, and you want to add this number to this number. Let's assume they're floating point numbers. There's a lot of inefficiency in floating point also that I don't want to go into right now also, but that's okay. Let's assume they're floating point numbers. Floating point addition is still very cheap, as you can see today. The question is, does it make sense to do 2 memory accesses to get those numbers into the chip, into the floating point unit, do the computation, and write back the result with another memory access to DRAM? You're basically consuming 3 times, 3 orders of magnitude energy of the little addition, which is really what you want to do. You don't want to move that data, really. Your goal is to do that addition and store the data. If the memory is able to do that over here, then you would save all of that 3 times 3 orders of magnitude energy waste, if you will. Okay, so that's the point. So if you actually look at that 3 order of magnitude worse here in terms of energy, if you go back, let's say 70 or 80 years, this is not an easy study to do. But let's assume that you tried to do this study, and we did. 70 or 80 years ago, this was actually much more expensive than this, because we didn't have 70 or 80 years of scaling of circuit technology on chip, which has enabled us to optimize this and put a lot of components, as well as reduce the energy of it. At that time, an addition, maybe not a double precision floating point operation, but an addition was about 2 orders of magnitude more expensive than a memory access. So we've come 70 or 80 years since then, and we've come 5 orders of magnitude worse on the memory side. Then the key question is, should we still be doing the same thing, meaning that bringing data into the processor to be processed, given that the trade-off has changed so much on this side? So why has this improved a lot over the 70 years? Essentially, it's the scaling, right? Technology scaling has enabled us to do computation with very little circuitry and very little energy, because we could reduce the size of all of those transistors in the computation unit, but they interconnected and scaled as well, right? Interconnect scaled very little, and certainly the off-chip analog interfaces did not really benefit from that scaling, at least as much. It did benefit a little bit, but not as much. So as a result, the interconnected and scale, analog interfaces didn't scale very well. This improved a lot, and this didn't improve a lot. Of course, we should make this more energy efficient, and people have actually tried that. There's a lot of research that goes on into the efficiency of the interface over here. So you could reduce this as well, but it's not going to be 20 picojoules anytime soon. Okay, so I've given you the 1000x, but we're going to talk about some other things. But there are some other studies that show that in the SoCs, which are one of the most heavily optimized systems for energy efficiency today, an add operation or a memory access costs about 2 orders of magnitude more than an add operation. So if you don't believe the 3 orders of magnitude number, this is results from other works that show that even in very energy optimized systems, you get about 2 orders of magnitude more energy when you're doing a DRAM access compared to an add. So 2 to 3 orders of magnitude, that's a lot. And we don't want to waste anything, actually. We don't want to waste 10%, let alone 2 to 3 orders of magnitude. And we've actually done some study, which I'm going to talk about. This is one of our recent works. Amirali is the lead author, where we analyzed the workloads, some important workloads to consumer devices at Google. This includes workloads like video encoding, decoding, TensorFlow, mobile, and Chrome browser. And we found out that more than 60% of the entire system energy is spent only on data movement. Basically, we have this energy budget that's really important for a device like this, and more than 60% of the time you're wasting it on data movement. Okay, well, more than 60% of that energy you're wasting. Basically, I think the conclusion is that we do not want to move data. We're moving data at the small scale and also at the large scale in the data center level, for example. We don't want to move any data. How do we do that? Basically, we need to get to a paradigm shift where we can enable computation with minimal data movement. And I call this a paradigm shift because it's really a paradigm shift. It's really changing the way we do computation and communication. We want to compute where it makes sense, as opposed to just in the processor. As opposed to having a processor-centric approach, we want to have a data-centric approach, or memory-centric approach, if you will, where the data resides. And it could make sense in the memory, it could make sense in the storage, it could make sense in the network, it could make sense in the processor sometimes also. Basically, we want to make computing architectures more data-centric. And that's the idea of processing in memory. So how do we actually do that? As I said, processing in memory is one example of processing near data or processing where the data resides. But it's a tough example because this interface is not really suited for any processing today. And actually, if you think about it, people have done a lot of research on storage. And storage folks always considered, okay, storage is a domain by itself. People have done a lot of research over here in architecture, and folks who design processors always consider, oh, this is a domain by itself, and memory was always in the middle. That's why it was kind of ignored. There wasn't a whole lot of, at least very forward-looking research in memory for a long time. There was, of course, but not as much as over here and not as much as over here. Okay, so what do we want to achieve? Let's assume that you can have memory that can store a lot of your data, database, graphs, media, whatever you would like over here, or data that you want to learn some model from, right? And you put it inside the memory, and we would like to be able to query memory and say, okay, we want a result from you. Give me the answer. And the memory returns the result back. Maybe an approximate result that the processor can query memory again on. Right? Or we would like to be able to query memory, can you do this operation for me? Basically have an interface that's relatively flexible such that we can ask questions to memory, including computations. We can ship computations there. So these interfaces today don't exist. So there are many questions over here that some of them we're going to touch upon. How do we design the compute-capable memory and the controllers? Where do we do the computation? Inside the memory cells themselves, or inside the peripheral logic, or inside the controllers? And how do we design the processor chip, as well as in-memory units, because maybe this chip becomes a little bit different if you have processing inside the memory. How do you design the software and the hardware interfaces to be able to do this? Today's hardware interfaces, as we talked about, they don't allow you to put queries over there, right? They allow you to read a location, write to a location, do a refresh, but that's about it. Maybe power changes, but certainly those are not queries. Well, I guess read is a query and write is a query at a very small level. It's not an abstract query. How do you design system software and languages once you actually have this sort of interfaces? And we're going to talk a little bit about that also. And how do you design the algorithms to take really advantage of it? Because today's algorithms are really very processor-centric algorithms. They don't assume any computation capability anywhere else. But if you have computation capability somewhere else, your algorithms need to change as well. And actually how you design the software needs to change, because some of the operations that you thought were very expensive become very simple right now. I'm going to talk about that in a little bit, like page copy and page initialization. So basically this is a problem that really spans the devices. How do you design the device itself, and actually the cells themselves maybe, and how do you design the algorithms? And there are a lot of questions over here to ask. So this actually, in-memory computation is not a new idea by itself, because people have actually thought about in-memory computation for a long time. One of the earliest papers, and if you think about analog computers that were designed earlier, they blur the distinction between memory and processing a little bit. But it never really was a big contender for general purpose computation. And actually one of the general purpose computation, the earliest work that proposed processing in memory inside the memory chip, by putting a processor inside the memory chip, was from Harold Stone at IBM. That was published in 1970. That's like 48 years ago now, right? And he called the design a logic in memory computer. 1970. So this idea has been around for a long time, but it's an idea whose time wasn't there perhaps. So today, as we discussed, there's a huge push from technology. DRAM scaling is at jeopardy, and industry is actually open to new memory architectures, which was not the case for a long time. And actually there are controllers close to DRAM. If we're going to talk about the 3D stack memory logic architectures, but basically you have a logic layer here that's connected to DRAM memory layers with what's called through silicon vias. So you actually have a single chip that contains multiple layers, and you can have very high bandwidth, low latency access to the memory layers through this logic interface. Okay, so that's one example, and these are the through silicon vias if you want to visualize them. And actually Micron has this automata processor where you can do operations inside the row buffer, very simple operations that they basically put into the hardware. These are deterministic finite automaton operations. So people are actually looking at how to use this also. It's very, very limited form of processing in memory chip that exists that I'm not sure if you can buy anymore. But okay. There's a pull from systems and applications that I just discussed. I'm not going to repeat, but basically what I just said earlier. So today is the right time to look into it. Then the key question is, how do you do it, right? What are the directions in which we should actually look at processing in memory? So I'm going to give you two possible directions. One is going to be something that has actually surprisingly not been examined a lot in the past. Actually, that has been examined very little. How do you minimally change memory chips to do computation that's perhaps very specific, but that could be very useful for those applications that do those computations. This is more like the accelerator approach. If we have the substrate that can do some things very, very cool, very, very fast, very, very energy efficient, with very minimal changes. How do we do that? So that has not been examined as much because people usually looked at, okay, we have this memory chip and we have this processor. How do we actually put the processor inside the memory chip? That's not an easy thing to do because if you really want to put a full-blown processor inside the memory chip, that actually, these two processes are very different in terms of manufacturing processes. Memory chip is customized for DRAM, capacitor, and in the processor chip you want actually high performance. Yes?
Just to understand like where we are, like it's not like the idea to have collaborating chips as a memory cores with each other, but more like a central CPU and like offloading certain operations.
Yeah, potentially. Yeah, we're going to talk about that. Yes. Basically, we're not going to get rid of the CPU necessarily, but we're going to offload certain operations in this minimally changing memory chips aspect. But I mean, if you take the idea further, if you exploit, maybe we can get rid of the CPU, or CPU could be just another agent around the memory. Okay, so let's talk about this first one over here. Okay, let me finish that idea. Basically, if you actually take a full CPU, for example, if you want to put it inside the memory chip, that's not an easy thing to do, because if you want a really high performance CPU, you really want a process that's customized for high performance. And the memory process is really not customized today for high performance. It's really customized for high capacity. How do you make that capacitor as little as possible, as less leaky as possible, as opposed to very high performance? And actually, whatever CPU you put over there is not going to be easy to make extremely high performance. Maybe you can put something very small over there. So that's why we pursued this idea of minimally changing memory chips. So, okay, what is the idea over here? What's the approach? It turns out DRAM, and actually any type of memory, I'm going to give you examples from DRAM, but there's a lot of work out there on emerging memory technologies that do similar things. Emerging memory technology we're going to talk about after this lecture. Memory has great capability to perform bulk data movement and computation internally with very small changes, because you can exploit internal connectivity to move data. We've seen one example of this in LISA, low-cost interlink subarrays. Actually, we added more connectivity for that. You can exploit analog computation capability inside the memory. And we're going to give a bunch of examples over here, some of which actually do the analog computation, some of which do some other things around the memory controller. Okay, let's start simple. Let's start with the minimal thing. And this minimal thing is not even computation. So it's always, whenever you have an idea, it's always good to ask, what is the minimal thing that we can do? And even when that minimal thing, what is the minimal operation that we can do? And minimal operation is really copying and initialization, if you think about it. You want to copy this page to this other page, or you want to initialize a page with some value. That doesn't even require any computation. And there's actually a lot of interesting work that has been published in the 1990s. Actually, one of these papers, I think this is from 1990, maybe ISCA 1990, where they actually say, okay, we want these operations to be fast, like page copy and page initialization, because operating systems use these a lot. And yeah, there are other papers that are also published saying that why aren't operating systems getting as fast as hardware? And there's people actually looked at bulk data movement, and these are some papers from Intel where they showed that if you do bulk data movement and copy with specialized hardware support in the memory control, you can gain a lot. We want to take this further. So data copy initialization is important. As you can see, there are many applications that could use it. Forking, you want to copy data. There's copy on write that happens in operating systems. Whenever you actually fork a process, you don't copy the page at that point, but you protect it. And whenever one of the children processes want to write to that page, or threads want to write to that page, you copy that page at that time. But you still need to do the copy. Initialization is important. All of the operating systems actually have zero-page pools where they initialize the pages in the background so that they can feed those to the processes that request those pages whenever they do memory allocation. And that takes time, clearly. And there are other applications like checkpointing, virtual machines, for example. Whenever you want to clone a virtual machine, you run into very similar issues, both initialization as well as forking. And page migration, if you want to migrate one page to another page inside the chip, you're slow, basically. And this paper that I mentioned earlier from Google, which analyzed their workloads and showed that you're waiting most of the time for data, it also showed that these two function calls, system calls, memmove and memcopy, are responsible for 5% of the cycles in the entire data center execution time of Google's workloads, which is really interesting. You may think 5% is not a big number. I may agree, but actually 5% is a big number for two reasons. One is these are only two operations, two function calls, system calls. There's a lot more other data movement that's going on in the system that are not necessarily due to them. And the second thing is 5% is a big number across very large number of workloads. And they basically really tested a whole lot of workloads in their entire data center here. And I'll give you one more bit over here. Sometimes in academia you get these papers that, for example, say, okay, we've improved energy efficiency of a processor by 30% by doing this little tweak. And this actually happened a lot in, let's say, 20 years ago, 30 years ago, maybe even 15 years ago, where people were trying to optimize processor efficiency. At the same time, they were improving with this little tweak the energy efficiency of the processor by 30%. Intel was saying there's no part of the processor that we designed that's consuming more than 5% of the overall energy. So there's no component where you can really tweak and get 30% improvement in energy efficiency. And I've seen these numbers actually, so what Intel was saying is not wrong. It was very optimized such that the energy was actually distributed across the components. So it's very difficult to do a tweak and improve something by 5%, by more than 5%. That's why this 5% is actually a big number. Because if you optimize things, you'll get 5%. And also, this is not data movement, as I said, right? This is really two function calls, two system calls only. There's a lot more data movement that may happen. Inside the application, for example, inside the application, you're not capturing that. The application may be doing its own copying with a for loop. And it's not captured in this. Okay, so how do we do this bulk data copy today? If you look at this page versus this page, and if you want to copy this page to this page inside memory, we go through the processor. Basically, we bring the source page byte by byte all the way into the L1. We bring the destination page byte by byte again all the way into the L1. We do the write, and then the destination gets written back into memory, which I'm not showing here. And that's how you do the write or copy. Now this is high latency because you're doing a lot of movement of data, as you can see. This high bandwidth utilization, basically if you're copying, let's say 4 kilobytes, which is really small, that's a lot of utilization of this bus. And while you're utilizing this bus to move the pages, nobody else can use this bus. So you're exacerbating the bandwidth bottleneck. This causes cache pollution because you're bringing the pages into the caches. But you could eliminate that today actually by doing this operation through the direct memory access engine. All of the chips that I know of provide access to direct memory access engine, where you could just do the copying through the memory controller. You need to set up and tear down that direct memory access, of course, which takes some time. But okay, you could eliminate the cache pollution today. And this caused a lot of unwanted data movement. What if you were just doing this copy and then you're not going to use the destination for a long time? Actually, this happens a lot in initialization, for example. Initialization is a special case of copy. Basically, you can think of initialization as initializing one page and copying the page to many other destinations. But if you're initializing, let's say, a huge database for whatever reason, you're not going to use all of those pages that you're initializing immediately. So you're causing a lot of unwanted data movement. And if you look at a small page copy, 4 kilobyte page copy, if you do it through the DMA with some technology assumptions, it takes about 1,000 nanoseconds today. And it consumes 3.6 microjoules. Now, wouldn't it be nice if we actually had support inside the memory that we could utilize when it makes sense? And the idea is very simple here. We basically tell the memory to do this internally and not disturb anything else in the system. It's called in-memory copy. And this is low latency because you can exploit the internal connectivity over here, which we did talk about, but we're going to talk about even more. You could basically save a lot of bandwidth because you're not moving anything on this bus. As a result, you're basically keeping it free. Somebody else who really needs it can access it. You could save cache pollution, but yeah, we could do that today also. And there's no unwanted data movement unless you really want the thing that you explicitly copied. Right? So there are a lot of benefits to having the option to do this in memory. Now, do you do it always? That's a different question. But today, we don't even have the option to do it completely in memory without disturbing anything else in the system. So I'm going to show you an example where we can reduce this 1,046 nanoseconds to 90 nanoseconds. Even this is not the best case. If you optimize it, you could go down to 70 in this technology. And this 3.6 microjoules to 0.04 microjoules. And the idea is going to be very simple. It's called row clone. And I think based on what you know about DRAM, you can come up with the idea yourself also at this point. Let's assume that the source row and the destination row are in the same DRAM subarray, which means that they're connected to the same sense amplifiers. If you want to copy the source row to the destination row, it's actually very simple. The idea is to first activate the source row, which brings the data into the sense amplifiers. Now the sense amplifiers have amplified the data and restored the source row. They have it strong over here. Now if you want to copy this data that's in the row buffer to another row, destination row, we send another activate, which implicitly deactivates the source row and connects the sense amplifiers to the destination row. And now the sense amplifiers drive the data that they've stored from row A into row B. Basically, this is the operation of DRAM, except we're taking advantage of it to do two consecutive activates, which essentially copies the data from the first activated row into the row buffer, and then from the row buffer into the second activated row. Very simple. Right? And the idea is two consecutive activates. It's negligible hardware cost. You could actually potentially do it in DRAM chips today, except it's not allowed in today's standards. That's okay. And I'm not going to go through this in detail, but this is what's happening at the circuit level, right? Yeah. The sense amplifier stores the data from one row, amplifies it, and then you disconnect it, and then the next activate pushes the stored data in the sense amplifier into the destination row. Very simple. And this is another way of looking at it. Okay. So this is source-to-source copy. This is copy within a subarray, right? That's why it's called intra-subarray. And this is very fast, as you can see. Now, what happens if the data is somewhere else? Meaning, if the source is in some bank, source row is in some bank, and the destination is in some other bank. Actually, source is going to be here, and destination is going to be here in this figure. We could use a shared internal bus, which was 64 bits, if you remember, from the Lisa lecture that I gave. What you could do is you could set the source bank to read mode and the destination bank to the write mode, and do essentially this. You could copy the entire row over here. It requires slight changes, but all of the circuitry is really there to do it. You just need to change the interface a little bit such that you could actually set this to read mode and set this to write mode at the same time. That's it. Does that make sense? So it's very simple. A little bit more cost than, of course, the subarray intra-subarray version of this. And it turns out you could still reduce the latency and energy significantly. I'm going to give you the energy and latency reductions in a little bit. And also, I think there's another interesting thing over here. If you go back to what I just discussed over here, source row and destination row, within the subarray, the copy is done at the granularity of rows. Right here, if you're across the banks, the copy can be done at any granularity that's larger than this bus, or multiples of that bus. It could be, if this is 64 bits, you can copy only 64 bits from here to here. You don't need to move all of those 64 bits to the processor, right? And you can copy basically at any granularity over here. So this is also a very powerful primitive, as you can see. You don't need to be always copying at the row granularity. Okay, so this is the generalized version. This is intra-subarray, two activates, consecutive activates. This is interbank, pipelined read and write across two different banks. And the worst part is really this inter-subarray copy. If the source row and the destination row were in different subarrays, well, too bad. What do we do? This paper, this row clone paper, proposed copying the source row to another bank, to a temporary location, and copying from that temporary location to the subarray over here, because there is no direct connection, as we've discussed, between these subarrays. But of course, you know a solution to this now, inter-subarray copy. Later, Kevin realized that you could connect these subarrays using isolation transistors, and that enables subarray to subarray data movement within a bank. So there is a new solution to this that is newer than the row clone paper. So I'm not going to harp on this as much. By changing the DRAM microarchitecture a little bit, you can do this inter-subarray copy. And we've already covered that inter-subarray copy. That's the Lisa paper, which also enables other stuff. So the area cost of all of this is actually very, very little in DRAM, 0.01%, because most of the circuitry really exists. Okay, so how about the initialization? I already said that row initialization, or initialization is a very special case of copy. basically can fix a row at 0. Let's assume that you're initializing a huge amount of data, 1 terabyte database, and entire memory. This actually consumes a lot of time when you do it. You can fix a row at 0 over here, assume that you fixed it, or you've written to it once, you paid the cost of writing to it, and now you can actually do row clone, right, to the entire subarray. And if you have Lisa, then you could do it across subarrays also. But zero initialization actually happens a lot that it may make sense to fix a row in a subarray to zeros or find other ways of actually doing that initialization. You can change the sense amplifier structure such that you can do this deterministic initialization as well. Okay, so this actually leads to significant latency and energy reduction for initialization with very little loss in capacity. Okay, so these are the summary benefits in terms of latency and energy of what I described. Intra-subarray copy now becomes very fast. You reduce the latency by more than an order of magnitude. Interbank copy, not as fast, but not bad. It's about 2x improvement in latency. And inter-subarray, you know that we have a solution to that, which is not solved in this work. And zero initialization becomes 6x faster. Initialization is a little bit less fast because when you're doing copying, you need to move 2 pages into the processor, whereas initialization, you need to move 1 page, right? Energy reduction, this is memory energy reduction. Again, intra-subarray is the best because you're moving the data the least, right? Whenever you actually start exercising more interconnects, your energy becomes higher. But in this case, the energy reduction with intra-subarray row clone is about 74x. Interbank, a little bit less. So this is at the entire row granularity. It's 3.2x over here. And intra-subarray, even with this unoptimized mechanism, without Lisa, you get 50% energy reduction, which is pretty good actually. And intra-subarray zero initialization buys you 41x energy reduction. So these are pretty significant numbers for things that are really simple today. And all of this comes at very low cost, very little increase in die area. And then the paper goes into, okay, what is the application level benefit from this? You can read the paper. I'm not going to go into the details a lot, but certainly there are some applications that do a lot of copying and zero initialization. And these may not be the most intense applications, although this fork bench can be very intense because you could actually make it a configurable workload, a synthetic workload that forks a lot of processes. And as you fork more, you do a lot more copying actually. And the paper has actually an interesting analysis of forking. Okay, so there's this is boot up. This is basically Linux boot up, profiling of the Linux boot up. Basically, there's a lot of zeroing and copying that happens when you boot up a system. And this is some shell script that gives you some directory entries, I think. But there's certainly a significant fraction of copying and zeroing in applications. And these may not be the most intensive applications, actually. Okay. So what is the benefit that we get in these applications if we are able to do intra-subarray row clone in them? The benefit actually is commensurate with the amount of copying and initialization that the application does. So these are the performance instruction per cycle benefits, and these are the energy reductions. As you can see, if the application is doing a lot of copying or initialization, you get a lot of reduction in terms of energy, as well as a lot of, this is memory energy, and a lot of improvement in IPC performance. So that's as expected, right? And if you want to see more analysis, you can read the paper, especially for this fork bench. Okay. Actually, there are interesting stories over here because when we first submitted the paper, it got rejected. And one of the reasons was, oh, you don't show benefit on spec workloads. Spec workloads are the workloads that are used by industry and academia to actually look at performance improvements, especially in the processor. But these workloads actually don't do a lot of copying of pages. So if you have an idea, maybe these workloads are not very representative, first of all. And the second of all, if this idea is not going to improve workload, why actually look at that? So it's always interesting to think about new workloads. So these are actually workloads that do a lot of copying, and this is where you really want to focus on if your idea is about that. I'm going to have another story about that in a little bit. Okay. So even an idea like this is basically doing processing in memory, right? It's not processing really, it's just data movement inside the memory. But even an idea like this requires end-to-end system support because the paradigm is not supporting it today. So what does that end-to-end system support entail? First of all, the application needs to communicate the occurrence of these bulk copy and initialization across the layers. You need to have this support in your instruction set architecture, for example. Now, fortunately, a lot of the interesting instruction set architectures have nice support for memory copy. For example, x86 has support for a memory move for a byte, but you could have the repeat prefix that tells you how many times you repeat this move. It's essentially a copy operation or initialization operation, and you can provide the number of repeats in a register, the count register ECX in x86. So that exists, fortunately, for copy and initialization, but it may not exist for other functions that we want to do in a little bit. How do you ensure cache coherence? So we didn't talk about cache coherence, so I'm going to very briefly mention this over here, but basically, if the processor is operating on this data, if it's already cached the page that you're going to copy inside memory, or the destination page, for example, or if it's cached the source page, and if it's written to the source page, how do you ensure that the memory is not really doing something wrong when the processor already has some data more up to date? And that's important. Whenever memory is doing something and the processor is doing something and they're operating on shared data, you need to ensure that nobody does anything wrong, and cache coherence is the substrate to enable that. So this is a good question. So in this work, in the row clone, for example, the idea is very similar to how the MA engines currently do it. So if you want to copy the source page to the destination page, first you need to flush the source page as well as the destination page into the memory, such that no piece of it exists in the processor caches. It's not the most efficient approach, but it's an approach that you can do in existing systems. Now, how do you do it more efficiently? That's a research problem, actually. If your processor and memory, they're both working on the same data, how do you ensure cache coherence in a very, very efficient way? Especially if you're doing a lot on the processing side, I think this is really interesting. And there's more work to be done in this area. How do you maximize the latency and energy savings? That's another question. Actually, before, who ensures the cache coherence is another question over here. Does it the software? Is it the hardware? Usually hardware approaches are much more efficient, but software approaches can flush the caches also. Okay, how do you maximize the latency and energy savings? This is also important because, as I showed you, latency and energy savings are very heterogeneous. If the source page and the destination page are in the same subarray, you get a lot of savings. If they're in different banks, you get less so. If you look at source page and destination page in the same subarray, you're more restricted. More restricted in the sense that you cannot do this copy at a granularity that's different from the row size, right? Which means that your latency and energy savings may not be maximized if your copy granularity doesn't match the row granularity, right? So who handles this issue? Basically, ideally, you would like to maximize the intra-subarray copies within the subarray. And if the operating system, for example, does a lot of copy on write whenever it forks a process. If the operating system knows the structure of the DRAM, if it knows the subarrays, whenever it's doing a copy on write, it can basically allocate the destination page from the same subarray. Right? So that's one way of doing it. Of course, those interfaces are not there today. The operating system has no idea about the structure of the DRAM today. But this is another reason why the structure of the DRAM should perhaps be exposed to the operating system. And if you're actually doing processing in memory, there's no question in my mind that you have to expose more information about the structure of the DRAM to the operating system as well as the application. Because if you want to take advantage of the benefits, the large benefits of processing in memory, you need to know that structure. And row clone is a very good example of that. And how do you handle data reuse? That's another question. Basically, if you're doing the copying inside the memory, now one of the problems is that if the processor needs the destination page, you may actually lose performance. Because if you did the copying inside the processor caches, you would have the destination page inside the processor caches, right? If you move that copying inside the memory, now the problem is you don't have the data in the processor caches unless you move the computation also to memory, but we're not doing that right now. So how do you handle the data reuse? I think that's a key question, actually. Whenever you have multiple different processors operating on data and they need the same data, you have not only a coherence problem, but also a data reuse problem. Where should the data be at a given point in time, such that you maximize the locality of exploitation of the data? So these are very interesting questions, and these actually span not just row clone, but any type of processing in memory engine. Whenever you're doing processing inside the DRAM or memory, you run into all of these issues, and they need to be solved somehow. And I'm not going to cover everything, of course, but you can find some works, and if they have the time, we'll get to that. Okay, I've given you this result already, but that's another way of looking at it. So that's the paper, and as you know very well right now, that the HPCA 2016 paper on Lisa improves upon this to ensure that inter-subarray copy within a bank is almost as fast as intra-subarray copy. So these two papers should be viewed together. Okay, so what about the algorithm? So I mentioned that I would give you another anecdote related to workloads. So if you think about how people deal with copies, so there are cases where you need to do a lot of copying. For example, in forking, system software companies need to deal with this a lot. For example, VMware is a very good example where they do a lot of copying for whatever reason. Whenever they want to clone a virtual machine, for example, that's a very good reason. And they see this downside a lot. And this is just 4 kilobytes, again. Basically, there's a huge, it takes about 1 milliseconds to do the copying, right? Okay, it's microseconds. I said 1046, okay, 1 microsecond to do the copying for 4 kilobytes. 1 microsecond is still a lot, especially if you're copying a lot of data. So how do you reduce it? One way of reducing it is actually put the burden on software. Software, basically, there are a lot of people who actually go and optimize the software such that you minimize the amount of copying as much as possible. And actually, if you look at the code that is developed by those companies, a lot of it is proprietary, but some of the public code is also there. A lot of effort is spent to minimize those page copies. And if you look at the resulting code, it's not nice. It's actually horrible. It's very hard to read, and it's very hard to maintain. Another benefit of pushing some of this work into main memory is now your code can become simple. Maybe you can say, okay, if it's 10x faster, I don't need to change my code. Meaning I do the simplest thing in my code and it runs fast. I don't need to jump through all of these hoops to actually get my code to avoid copies, which makes my code as a result unmaintainable, maybe even unreadable almost. Yeah, so there's basically effect that this sort of hardware support can have on the software side that's really not quantified, and I don't believe it's really quantifiable in any academic paper that anyone can do. It's very difficult to do those studies clearly, right? But it's really important to think about it. If you had this piece of machinery, how would your code change? Make sense? It's a chicken and the egg problem because this machinery is not there. As a result, we write the software this way. But if you have some other sort of machinery, you would write the software in some other way. And whenever people are evaluating new ideas, they should be very cognizant of this actually, because you may shoot down new ideas easily because existing software doesn't behave in some way. But if actually some new idea enables a different way of writing the software, which you may not be able to thinking about at that point, that new idea actually may be really good in the medium to long term. Right? Another example of this actually, I'll give you another anecdote. Intel in the 1990s, when they were designing processors, it's a very processor-centric company, no question about Intel, right? There were no accelerators almost at that time, if you think about it. Floating point was actually an accelerator. Initially, FP units were accelerators that were outside the processor, and they got incorporated into the processor. That's why it was an accelerator. But they were having a debate, very fierce debate in terms of, oh, should we put these vector extensions, SIMD extensions, which we talked about earlier, into the processor? And the debate was, who's using them today? And if you looked at who's using them today, well, there would be 0 people because there are no extensions, right? And these are the MMX extensions, multimedia extensions. This is like, maybe Zürich is not the best place to talk about it, but okay, Zürich may be the best place. There is this bridge from Rapperswil to, I think, Pfaffikon at the end of the Zürich Lake. There's a bridge, right? Now, you could say, okay, we want another bridge over there. And the question you may ask is, okay, who's using that other bridge right now? That's the wrong question to ask, right? The right question to ask, who may be demanding that bridge? This is actually interesting. So you could do the study of who's using that bridge, and one way of doing the study is actually very interesting. You could do that. You could go to that location where you want to put the bridge on. You could take your, I don't know, boat, and you could, for a day, sit and observe who wants to cross the lake with their car at that particular location. And you could count the number of people, right? And you would get a number. Now, is that number a good number? That's a different question, right? So that's one way. So I think that's the difference between the forward and backward thinking and asking the right questions. And you will be amazed how many people ask the wrong question whenever there's a new idea. You really need to be asking the right question. So clearly there are 0 people trying to cross that bridge. Maybe some people. Or of course you can doctor that number also by adding more people, right? Getting your friends to try to cross that bridge, cross that location at that point in the lake. But anyway, you get my point. So basically there was a lot of debate at Intel as to whether they should put in this MMX extensions into the processor. And there were a lot of fights internally as far as I understand from the people. And in the end, they did put it in. And it was the right thing to do, if you think about it, right? Those MMX extensions are actually some of the things that have improved the systems a lot compared to many, many other ISA changes that have happened over the years. And those MMX extensions are going really strong right now. They're AVX. They've been widening. They've been becoming more powerful over time. And those are being used not only for multimedia workloads. The initial thought was actually, okay, we'll use these for multimedia workloads. These multimedia workloads are there, image processing, video processing. People are doing it. The general purpose processor is not good for doing it. So if you had these SIMD operations that can operate on multiple elements of data, we could offload those operations and you could get a lot higher performance at higher efficiency. So it's a very reasonable argument. And if the answer is, if the question is, okay, who's using them right now? Clearly 0 persons. As a result, you won't do it. But if your question is, okay, who can use it in the future, then you'll probably get a lot. And you will actually, once you actually incorporate that extension, you will also find that people you never imagined would be using it could be using it in the future. Like we've used those extensions for bioinformatics workloads, and I don't think anyone has thought about using them for bioinformatics workloads when they actually were proposing the implementation of it. It was mainly for multimedia acceleration. In fact, it was called MMX, multimedia extensions at that time. Now it's called advanced vector extensions, which is more general, of course, and everybody is using it for code that is vectorizable in that sense. Okay, so I've given you this longer anecdotes because processing in memory is another example of this, right? Who's using processing in memory today? Clearly 0 people because it's not there. Who may be using it? It's good to think about it very carefully, but not extremely carefully, because if you actually take the step and actually do it, maybe you'll find a lot more people using it very quickly than you might imagine, right? So there's a leap of faith in architecture also. If you don't build this building, nobody's going to use it clearly, right? And nobody's going to like it. But if you do build a building like Oculus that I showed you earlier, initially people may complain, okay, why spend $4 billion to do this? But once they're in there, oh, this is the greatest piece of architecture in the world. And they would start taking pictures and everything, right? So that's the mentality. And that mentality is very important to set right, I think. Okay, now that we've set the mentality, let's go on. Basically, we're thinking of memory as an accelerator. Now today, actually, we have a lot of accelerators, and I've talked about SIMD accelerators, which is inside the CPU core. But there are other stuff over here. There's video, imaging, GPUs, whatnot, speech. And their goal goes to the memory controller, as we've discussed. And they're all sitting on this left side of the memory bus, which means that they're all bottlenecked by the memory. Whereas memory itself, if you think of it as an accelerator that can do specialized computation, it's really not bottlenecked by this traditional bottleneck. This is also called the von Neumann bottleneck by some people. I still like the memory bottleneck or memory bus bottleneck because there's no reason why this should be called the von Neumann bottleneck. I think von Neumann did a very good system design for his time. But maybe memory bus was not very easy to predict 80 years later. Anyway, basically you can actually put specialized computation capability inside the memory and you will not be bottlenecked by the memory bus. So you have access to ample amount of storage with ample amount of bandwidth and with very little latency. So why don't we think of memory similar to a conventional accelerator? And we could potentially program it with mechanisms that we've developed for these accelerators, at least initially. And then we can actually expand the programming models for this to be much more data-centric as opposed to accelerator-centric. Okay, so now I've given you mechanisms for doing no computation in memory. It was just data movement and initialization. Let's talk about mechanisms for doing other stuff. So we can do copy, zeroing. Can we do and or not and maybe majority function. This will be obvious when I talk about majority. Why am I introducing majority? But we can do it at low cost. Again, we're going to use analog computation capability of DRAM. I'm going to give you the idea very soon. I'll give you the high-level idea. If you can activate multiple rows at the same time in DRAM, this actually performs analog computation due to charge sharing. And we're going to exploit that analog computation capability. And I'm going to show you significant results, like 30 to 60x performance and energy improvement because of this, due to in those operations. And this paper was published in Micro 2017. Okay, after I give you the idea, make sure that I tell you the story about this bridge in a little bit. Okay, new memory technologies, actually, which we're going to talk about in a little bit, enable even more opportunities, actually, in this domain. We're going to talk about some of them, not in the context of in-memory computation, but some of these technologies are very compatible with logic, and some of them actually can do computation without moving data at all. Because these are non-volatile. Whenever you access data, you don't destroy the data. In DRAM, whenever you access a row, you destroy the row. You have to fundamentally move it somewhere else if you want to keep it. So fundamentally, DRAM is not the minimal energy substrate for in-memory computation, because you have to move a little bit. Whereas these technologies are fundamentally more suitable for really data-centric computation, because you don't even need to move the data when you operate on it. Okay. So let me give you the idea of how to do AND and OR in DRAM. Basically, the primitive is triple row activation. You know how to activate one row. You know how to activate two rows in a consecutive manner. And then in tiered latency DRAM, we actually activated two rows at the same time also. Now we're going to push it to 3. If you can actually activate 3 rows concurrently at the same time, what happens? Basically, in an ideal circuit, if 2 of these cells are charged, you'll get the charge state at the end. That's the animation over here. If 2 of these cells were discharged, you would get the discharge state at the end. Now what is that? That's really bitwise majority, right? Basically, in an ideal circuit without a lot of variation, what you would get is a bitwise majority. And you do it bitwise, and you do it in a bulk manner, because the entire row operates exactly the same way I described. So bitwise majorities are very interesting, actually. People have built a lot of CAD tools, and they're building a lot of CAD tools today based on the bitwise majority circuit. You can map a lot of circuits into majority circuits. And if you're really interested in this, Knuth, I think, in his fourth book, talks about the beauty of the bitwise majority function. That's nice. You could do, perhaps if your computation was consistent of bitwise majority, you could directly map it to the substrate. But there's even more interesting things here. If you actually rewrite this Boolean equation with what you learned in digital circuits, it's a very simple rewrite. You get this. And this basically tells you that if you set C to 1, you get the OR of A and B. And if you set C to 0, you get the AND of A and B. And by controlling what you put to C, that row, you get the bitwise OR or bitwise AND of 2 other rows. That sounds nice. Now we can do bitwise AND, bitwise OR. That's actually very nice, very useful for some applications which we're going to see. But it's not functionally complete. Okay, before that I'll show you an example of how you could potentially incorporate this into the ISA, right? So this is one example. If you want to do bulk AND of row A and B and write the result into row C, this is the semantics. That's what I just said. Implementation, of course, you need to be very careful. How do you actually ensure this? So what we do is we designate 3 rows for triple row activation in a subarray. So if you want to do triple row activation in the entire subarray arbitrarily at any row, that's actually a lot of cost. Why? Because you need to have 3 row decoders into the entire subarray, and that's a lot actually. So if you have designated rows, actually that row decoder can be much smaller, and that's the idea over here. Most of the subarray, you can do only 1 row of activation, but there are some designated rows where you can do triple row activation. And if you want to do triple row activation on any other row, you first need to bring the rows into that designated area. That's the idea, and the paper has more detail. And the paper also proposes having reserved rows for 0s and 1s, because those enable ANDs and ORs, right? Okay, so how do you actually do the bulk AND? This gets translated internally in the memory controller to a row clone of A into one of these designated rows. So from that part in the subarray, you take A, put it into D1, and you do row clone for that. You need to row clone the other source row into D2. And since we're doing an AND, we need to set the third row to all zeros because of this Boolean equation, right? And requires C to be set to 0. As a result, we row clone the reserved 0 row into D3. Now all of the inputs are there in the designated rows. Now you can do triple row activation in the designated rows, minimally affecting the subarray. Now the result is in one of these rows. Because of chart sharing, all of these rows actually have the same result. And you row clone the result from any of these rows into the destination row C. And that's the idea. And you can see that this builds on row clone. Without row clone, this wouldn't work because you don't know how to get the result out. Or it becomes very expensive, meaning you need triple row activation in the entire subarray. And 3-row decoder is a big no-no in DRAM. That's a lot of row decoders. And actually, how do you lay it out becomes even worse if you actually have 3-row decoders. Okay, so this idea was introduced in this short paper. And then the problem here is, AND and OR is great, but it's not functionally complete. Meaning that you cannot map any computation into just ANDs and ORs, right? It's not Boolean complete. For you to be functionally complete, you need an AND, or an OR, or AND and NOT, or NOT, or and NOT, right? So basically we need a NOT in this case. I don't know how to do an AND or NOR. If you figure out how to do an AND and NOR inside the DRAM, you might be golden. Just talk to me. People have actually figured out how to do NORs inside memristors. There are papers called Magic, for example, which are purely based on NORs. Inside a memristor, you can do a NOR. And basically, once you can do a NOR, you can put any computation inside a memristor. It's very interesting. We may talk about that, but I'm not sure if we will have time. So in DRAM, we cannot do a NAND and NOR easily, so we want a NOT. So how do you get the NOT? This is a little bit more costly part. But this NOT actually already exists. So remember the sense amplifier? Whenever you sense something, the bit line bar is on the other end of the sense amplifier. The problem is it's not connected to anything in the subarray. So we're going to try to connect it. That's the idea over here. Basically, the idea, high-level idea, is we want to feed the negated value that you've already sensed. So you activate a row. The row is inside the sense amplifier. And complement of the row is also inside the sense amplifier, complement of that bit. And we want to connect that back into the subarray to some other row, let's say. And how do we do that? Basically, this is how we do it. Into a special row, we connect this bit line. And this is the bit line connection. I'm not going to go through this in detail, but basically, if you activate this word line over here, you capture the value that you have in bit line bar into this destination word line. It's a bit more cost because this is somewhat special compared to other rows. And also, there's some interconnect cost that you need to pay to do this connection. And according to the results in the paper, it's about maybe 1% cost total. Of course, it's very hard to figure out the exact cost without really building this. But building this is really hard also, especially at the technology levels that DRAM has gone into right now. But at the idea level, it makes a lot of sense. So how does it work? Basically, this is the initial state. You activate the source row, which brings the data over here, and it gets amplified. And then you activate the D line over here, and then the N word line over here, and so such that you can capture the data from here into this special row. You can read the paper for more detail, but essentially, you bring the negated value into a special row, and then you can copy it anywhere after that, right? That's the idea. Okay? You can convince yourself that this works after the lecture. And there's a lot of circuit simulation in the paper showing that this works, and this works reliably. Okay. So what is the benefit of it? The benefit is actually a lot of high throughput inside the DRAM for these operations. This is comparison points. This is Intel Skylake at the time, a GPU at the time, and hybrid memory cube, which is the 3D stacked logic and memory. Clearly, if you do logic operations inside that logic layer, you have access to a lot of banks in that hybrid memory cube. As a result, you can do that at high bandwidth. So that's the 3D stacked approach, which we're going to talk about more. So you can see that the bandwidth is very high in hybrid memory cube. And this is Mbit without 3D stacking. Inside the DRAM module as is today, if you add whatever we described, you're better than logic layer approach. And it's still commodity DRAM almost, with some changes, of course. And if you actually do it on 3D stacked, because 3D stacked buys you a lot more bandwidth, a lot more banks, you can actually do this in parallel in many, many banks. As a result, your throughput actually at the time is, for knots, for example, you can do 2 tera knots per second, assuming some parameters, of course. And that's much higher than a CPU and a GPU at the time, as you can see. So that's the benefit. So you can do this inside a single DRAM module, meaning that all of your subarrays could be doing this computation. So it's really parallel. The real limit is how much you can power up this chip doing all of that computation, right? But we know how to power things. We're designing these GPUs that can do a lot more computation actually, internally. In DRAM, we're still doing computation. But so basically, you need to put the substrate such that you can power up the chip and you can also cool down the chip. Clearly, if you put computation inside a memory chip, you don't expect power to remain the same. So you need to put, of course, create the infrastructure to ensure that you can sustain that power as well as the cooling mechanism. But that's easy, I think. We know how to do that from the CPUs. If you are able to do that, you can get to very high bandwidths in a parallel manner. Ideally, you would like to do this in every single subarray, right? That gives you the highest parallelism, assuming your problem actually is doing it. It requires that much data throughput. Okay, so NOT and/or is a little more complicated, of course, because you do a lot of row clones, whereas NOT is less so. Now you can build NAND, NOR on top of these, and XOR and XNOR. Basically, you can do any operation after this, right? This is really a functionally complete system. Whatever application, whatever problem you have in mind, you can map it to this. Will it be efficient is a different question. We'll talk about that. Okay, so what about energy? The performance numbers look good. Energy numbers are actually quite good also. This is compared to DDR3 channel energy. And you can read the paper for more detail, but essentially you reduce the energy of a NOT by about 60x. And you can build up an XOR and XNOR by about 25x, which is still quite good. And this is the summary. I'm not going to go into the detail. So the question is, you can map anything into this, but what really runs very efficiently in this? So if you're doing a lot of bulk bitwise operations, it's a perfect substrate. Right? And who does bulk bitwise operations? Well, it turns out there are a lot of people who do bulk bitwise operations. So database indices, for example, I'm going to show you an example of bitmap indices. You can actually express your database in terms of bitmaps such that you can query things much faster. Web search, actually you can design your database such that you maximize the number of bitwise operations you do. And there are databases that are designed, bitviewing is one example over here, with the purpose of using GPUs that are really good at bitwise SIMD operations today compared to CPUs. Or SIMD operations, not just GPUs. You can use SIMD operations also to do bitwise queries, right? So there are databases that are designed for this purpose. So we're going to look at that very quickly. Microsoft actually is doing something similar for their web search engine. They've designed this Bitfunnel engine where they want to use the SIMD operations or GPUs to accelerate web search as much as possible. So there are a lot of bit operations over here. DNA mapping, which we're going to talk about actually. I think Mohammed talked about the Grim filter approach a little bit. That approach is essentially processing in memory that can take advantage of Ambit over here. And encryption algorithms and other operations, set operations are covered in the paper, so you can take a look at that. I'm not going to talk about that here. But I'm going to focus on these two as examples. Although I believe there are many, many more examples. Once you have the substrate, you can also start thinking about your problems your problem such that you can write it on the substrate, right? Again, this is a chicken and the egg problem. Today, many algorithms may not be using bitwise operations because there's no substrate. Now, SIMD operations are there, GPUs are there, they're very powerful, they're bitwise, and people realized in the database community, oh, maybe we should take advantage of them. So how do I rewrite my database such that it executes efficiently on the GPUs and SIMD? And they've essentially done this. Why? Because GPUs are so prevalent and they exist. Right? So a chicken and the egg problem. Okay, so one example is this Bitmap Index. This is an alternative to B-tree and its variants. This is efficient for performing range queries and joins. If you've taken a database course, that's good. If you don't, at least you will understand the example that I've given over here, that I'm going to give. So basically, you can represent your database using these bitmaps. For example, you can have an age field, and as opposed to just storing the age, maybe you store that also, but in addition to storing the age, you can classify it somehow into groups. Basically, the rows include the database entries, let's say people, let's say students, and you classify the students as bitmaps based on the ages, and you basically have a bit set to 0 if the student is less than 18 years old, a bit set to 1 if they're not less than 18, well, the other way around. The bit is set to 1 if the age is less than 18, otherwise it's set to 0. So basically you have a huge bitmap. If you have 1 million students over here, this bitmap is 1 million long. And you can have different categories over here. And you can also represent other information. The student attends ETH, the student lives in Zürich, or different places. Basically you have a huge number of bitmaps, and the query is very simple right now. If you want to query the students who are within this age range, who live in Zürich, who make this much money, it's essentially bitwise AND and ORs and reductions, right? That's all you do. And there are databases that use this, and we ported those databases. And you can see this is the speed up in terms of the execution time of the query. It's 5x to 6, 7x. That's a lot of speed up. And you can read the paper for more detail. I'll give you another example. This is Bitweaving. This is a database that was designed by folks at University of Wisconsin, Jignesh Patel's group. We ported that into Ambit. And you can see that this is the speed up that you get in a query. It's about 12x. That's very significant. It's not easy to optimize your database to get 12x speed up. And I'll refer you to these papers so that you can take a look at it. I've covered a lot, I think. So basically, the challenge and opportunity for the future is computing architectures with minimal data moment. And I think this is an example. I promised you an anecdote before we leave, but this anecdote is also very telling because we got exactly the same comments. Actually similar nature of comments. So this paper was actually rejected 4 times before it was published for the 5th time at Micro, which is a top conference. So if you're writing papers and you're getting rejected, don't give up. Because if an idea is good, then it's important to put it out. So the reasons for rejection, I'll tell you 2 of the reasons. One is, who uses these bulk-bitwise operations? This is very similar to the answer you could have gotten to the bridge question, right? Are there enough applications that use? Again, if you don't put it out, maybe there will never be enough applications that use. That's one thing. So I find this comment very backward looking, as you can see, because people are actually developing those bitwise databases because GPUs exist today. If you had a substrate like this that existed, people would be developing even more, perhaps. So clearly, one paper, don't ever expect one paper to solve all the problems in the world. If we actually had to solve that problem and figure out, develop applications that actually were written using bulk-bitwise operations, that would be a lifetime project, perhaps. That's the first big comment. The second big comment is actually maybe even worse or similarly worse. It says basically the reviewers said, oh, DRAM, this is a great idea. Actually, the reviewers acknowledged that this is a great idea. They really liked it, they enjoyed it, but DRAM manufacturers will never implement it. So that was the reason for rejection. So you can see that mentality, especially if you come up with very different ideas, is sometimes really warped. Okay, how do you know that DRAM? First of all, how do you know? Is this a really scientific comment? It's not. And second of all, assuming it's a scientific comment, how do you know that somebody will not implement an idea if the idea is not out there and published? So it's good to keep this in mind. Whenever you generate new ideas, you'll get these naysayers who will try to kill the ideas. And this is not just in academia, actually. This is true for every aspect of life. If you're generating new ideas, you should be ready to be rejected. But the new ideas can actually prove themselves in the field. So they're actually interesting things that are happening in the DRAM as well as emerging memory technology field that look very similar to what this might be. Okay, any questions? Maybe I'll leave you with this then. I've given you a lot of anecdotes for especially mind setting, but next time, meaning tomorrow, we'll start with 3D stacked memory. Okay, I'll see you tomorrow.